Okay, in addition to alcohols, we can use something called a diol, and what this simply is what the name implies, is that there's two alcohols in the same, or two alcohol functional groups in the same molecule. So first, in naming these, it's actually pretty simple. We just list the numbers, and instead of just saying all, we say it's a diol. So this would be 1,2-cyclohexanediol. This here would be 2,3-pentanediol. Now, this is a common name. This is actually just antifreeze, and we typically call that ethylene glycol, and that's a very typical type of name that you'll hear, so that's okay that it's a common name. It's not an IUPAC name, but you probably still should know that one. We can synthesize these through two different means, just as we talked about, reduction or oxidation. We can do these through reduction or oxidation. So we can start with a diketone or aldehyde, any type of C-double-O bond. Through H2 and PDC, remember that'll make the OHs. We can use lithium aluminum hydride followed by water, and that'll make the OHs. Or we could just use the NABH4 methanol. That will do it. Ethanol is fine here too. Or we can go through what's called an oxidation. So there are some typical types of reagents for oxidation, just as there are typical types of reagents for reduction. In this case, with a double bond, you may have seen this in Orgo 1 too, we can use osmium followed by NMO, and that will give you a syn diol. So in other words, the diols are going in the same direction. So we can actually be stereospecific with this. And you'll get its enantiomer as well, obviously, too. You can also use KMNO4 followed by NaOH, with NaOH, and it'll give you those as a syn reaction. To get an anti-addition of two OH groups, in other words, you get them going in the different direction. So one's going towards you, one's going away, and it's an enantiomer. You would start by, well, there's actually several ways to do this, but in this case, let's think about this as a more simple way to do it. Starting with MCPBA, or a peroxy acid, which I think you've covered in Orgo 1, and that's going to give you an epoxide. You could then go through and add either an acid or a base to yield these OH groups. And the mechanisms, you'll see why that's the case if you look at those mechanisms. So, if we're going to look at other ways to prepare alcohols, one of the important ways is by using a Grignard reagent. And Grignard reagents are very specific reagents that are great for a lot of things. And what we start with is an alkyl halide, usually an alkyl bromide, but it can be a chloride too, but we usually start with an alkyl bromide, and we simply add magnesium to that. And what that forms is it forms this Grignard reagent. The magnesium wants to take on a partial positive charge because it's a metal. That means that this R group takes on a partial negative charge, and it becomes a very good nucleophile that can attack. And so when we look at the mechanism and how these things work, first I want to point out that this is a carbonyl, right? So we've got a C-double-O bond here. In this molecule, the oxygen is what was trying to grab the electrons. So there's a partial negative charge at this oxygen and a partial positive charge at this carbon down here. So this guy is ready for a nucleophile to come in there, right? So he's ready to take this guy on, and electrons pop up. And when that happens, you end up with this guy right here. Well, since there's a negative charge, you then, and only then, want to have some type of proton source around, such as water. Well, these electrons will come and grab that hydrogen, and electrons go away. And that ends up negating what's coming over here. So it's just basically a salt. And you end up with an alcohol. Well, this is really super duper awesome, because now we can do all kinds of things, but you have to make sure that your water comes last, because actually this guy's pretty sensitive to a Grignard, or to water, and here's part of the reason why. It'll do the same thing to carboxylic acids as it kind of does to water. and that this is my nucleophile, and it ends up finding a hydrogen to react with. And so you end up getting this guy, which doesn't really react, and you just wasted your R group here. So there's no overall reaction here. That's what happens with water too, so you have to be very careful. Now, let's say that you want to use a Grignard reagent, but the problem is that you've got something else in your molecule that's going to be sensitive. Well, we want to use a protection group, and this is something that we're going to see throughout the semester, but protection groups are very common in organic synthesis to be able to target and get the reaction to occur where you want it to actually occur. So they can cap one protection or one type of group or functional group while your other functional group reacts the way you want it to. So a protection group for an alcohol is typically this TMSCl. Now, with a protection group, you also want to be able to remove that protection group. So for an alcohol, we use TMSCl, and this is triethylamine, or TEA is another way that I call it. It's just a simple base. It's an organic base that's easy to get out. And so we end up putting this trimethylsilicon at the silicon at the end of this oxygen group. And what that ends up doing is it gives it this big, huge bulkiness. And so the oxygen's just not as willing to react as what it normally would be. We can remove this TMS type of protection group by using something called TBAF. And yes, this is like an ammonium fluoride. It's tetrabutyl groups. It's got all over it. Don't worry about what the actual structure is. The point is that it takes off that protection group and leaves you with an ROH. So here's how we can use that, right? Let's say that we make something like this. And we want to be able to use this guy without him reacting. Well, what we can do is we can use TMSCl and TEA, or triethylamine, same thing here, and we end up with this OTMS group, right? Well, now we can turn this into our Grignard reagent, because now we can just add Mg and make that happen. And then whatever type of C-double-O bond we end up with here, you can end up adding it right there. See how I did that? So here, this is my nucleophile. It comes in here, and these end up down here. See that? Followed by water, that makes this an OH. And then we can add TBAF, and bam, we end up with 2 alcohols. That's pretty cool. Okay. Next, we're going to go through a lot of ways to react with alcohol. So traditionally, and this should be a review from Orgo 1, we could take an alcohol and react it with an acid. What's going to happen is that this OH comes and grabs that hydrogen, electrons go back, and basically you have a water molecule that's stuck there that can leave. Then your nucleophile, no matter what that is, can come in here. Or actually, it's usually this X that's over here, so X being a halogen of some sort. And that's what you end up with right there. But the problem with this type of thing is that you can have things rearranged, because anytime you go through a carbocation, you can have rearrangements. So let me stress that again. Anytime you have an SN1 or you go through a carbocation in the mechanism, you can have rearrangements of that molecule. So here's an example. Once we hit this with HCl, you end up with a positive charge right here. Well, this is a secondary carbon, and right next door, there's a tertiary carbon. I often say when it comes to positive charges, it's kind of like something being broken. So let's say that you just broke your ankle in the middle of a field. Do you want to have 2 friends around to help you? Or would you rather have 3 friends around to help you? Because I want 3. So what ends up happening is a hydrogen that could be right here can shift over. And when that happens, you end up with a positive charge there instead. So this is a more stable arrangement, and that's why that happens. So chlorine would then come in here, and bam, there you go. Okay. Now, on the other hand, if you have an SN2 reaction happen, you're not going to get those rearrangements because first this comes in here, and that goes there. And then these happen at the same time. It's a concerted step. At the same time, one's leaving and one's coming in, which takes a lot of room, if you recall. But that means that there's not going to be a positive charge here to rearrange. So you end up with this bromine right over here. If you're using HCl, by the way, on this, you probably want to use zinc chloride. It just helps catalyze that reaction. Okay, some more reactions to go here. We're going to use pyridine in a lot of these. So pyridine is simply an organic base. It's easy to remove, and that's why we use it quite often. So here we go. If you have an alcohol that is stereospecific, you definitely don't want to lose that stereospecificity. And so we try to use an SN2 type of arrangement because that will give you a stereospecific product. It costs a lot of money to get a particular stereo arrangement, and so once we have it, we don't want to lose it. Okay, so a way to do that is to simply take this OH and turn it into a better leaving group. Once it's a better leaving group, then you can have a nucleophile come in and it will give you the backside attack and you'll end up with that product. So here's the mechanism for that. This TSCl looks like this. Okay, so what's happening is that these oxygen electrons are coming here to that sulfur and the chlorine is leaving. That then gives you a positive charge right here on the oxygen, and then the pyridine that we put in there comes and grabs that hydrogen and electrons go back to the oxygen. Well, now this guy is a really good leaving group. So nucleophiles will go in there pretty easily, bam bam, and there you go. You have to be careful though. If you add a strong base instead, you can end up getting an elimination reaction here to give you a double bond between these two carbons. So just be a little bit careful with that. Okay. Almost done. Last page for today. You could also use PBr3 or PCl3 with pyridine in order to get either Br, or if you use PCl3 you get Cl there too. So this is another type of reaction where you end up with the backside attack occurring because it's an SN2 reaction. And here's how it works. You'll see that it's pretty similar. Electrons go and attack that phosphorus, and then, I'm sorry, let me correct that. This bromine leaves, or a bromine leaves, and you end up with the oxygen here connected to the PBr2 and another hydrogen right there. So the pyridine comes in, grabs that hydrogen, electrons go down. Bromine then comes in, backside attack, this kind kicks that guy out, and bam, you end up with the bromine from the opposite side. Sorry, it is going on the other direction, so that's a dash line. SOCl2 with pyridine does a very similar type of thing. I always use it, we like to call this suckle, because it sucks it to it. I don't know, it just works. So SOCl2 and pyridine ends up giving you this. Here we go. These electrons come and attach to the sulfur, chlorine leaves, and then you end up with your alcohol attached to the sulfur. Oxygen has a positive charge to it. Pyridine comes and grabs that hydrogen, electrons go back, and then chlorine comes and attacks. So where the chlorine come from? It came from over here. So here we go, and then bam, then you end up with the chlorine right there. Now, POCl is another one, so POCl3. At 0 degrees with pyridine, we could actually take the alcohol and turn it into a double bond. So this is sort of the opposite of that reaction, in that you can simply take this guy, and he's going to attack this phosphorus, and the chlorine leaves. Here, though, we're going to use two equivalents of pyridine. So first, this nitrogen comes and grabs that oxygen, or that hydrogen, excuse me, and electrons go back. And so now we've got a really good leaving group again, but this one just wants to do something different. So this pyridine comes and grabs this hydrogen from the next door, and then an elimination occurs, and you end up with that double bond right there. Thank you very much.